In this lesson, we're going to discuss volumes of revolution. And to revolve something, right, we're going to take this curve. I'm going to contrast one function revolved about the x-axis versus that same function revolved about the y-axis. We'll talk about the mechanics of how that works and what this means in general. So first, just the idea of revolving it about an axis. It just takes a curve, and then, in this case, revolving about the x-axis, takes every point and allows it to, you can imagine from that point, if you measure the height of this, if we now took that green line and from the board dropped it down so that it made a circle with this green line and just swooped it all the way around and then through the back side of my two-dimensional surface here. So effectively what this thing will make is kind of like the bell on a trumpet, right? A horn, if we revolve it about the axis. So let me be a little bit more specific with my picture. Let's say that we're going to go up to an x value of, I don't know, 5. So we take our value here, which of course is 25, and then we revolve that thing about, my picture's not very sweet there, but revolve it about the x-axis so that it makes a circle. And what I'm trying to do here is create the same thing on both the x and y-axis. So now, if you were looking at the front side of it, you would just see this one circular disk. Again, the function is kind of hidden behind it. And there's all kinds of little circles hidden right in here. So there's the vision of it. Now we're kind of able to look inside the trumpet bell a little bit. So now let me go back to the original picture. Hopefully you have an idea for what that thing is supposed to look like. If you don't, there's all kinds of things on the internet if you just Google volumes of revolution. Little YouTube videos or whatever, but also textbooks have really nice pictures of them where they're all shaded and all that kind of thing. So anyway, the first disc, I'm going to draw it sort of thinner now. The first disc on our trumpet, if we wanted to find the total volume of this whole object, what we're going to do is, just like with integration, how we took little areas of rectangles, we're going to add up all of these little areas of the circular discs. So imagine we're taking our little horn, and by the way, the horn is filled in, right? That's so that we can interpret its volume. And then we're just pushing it in through the deli slicer, and it's going to chop off one slice at a time. Every slice will be circular. And that's because it's a volume of revolution, right? It's doing one revolution about the x-axis. So if we take all the areas of those circles and add them up, now there's infinitely many of them. If we slice them really thin, infinitely many little circles, if we add all those things up, we'll have the volume. Now you might think, well, how are you going to add area up and have volume? Remember what integration does, though. So what we're going to do is we're going to basically integrate the area of each disk dx, right? From, in this case, 0 to 5. And the basic task here is to find that area. And to address your concerns about going from area to volume, remember dx, that's going to effectively be the thickness of each circular slice times area, and now you get a volume unit, right? So these will be in square units, and that would be in units, so we have cubic units, and when we add all those little cubic units up, we get a volume. So imagine again to the deli slicer analogy, imagine you ask them to take the little cheese block or wedge or whatever and cut it thick, you know, maybe a 1/4 inch or an 1/8 inch thick, which would be a pretty thick slice of cheese for a sandwich. And then you said, well, actually, I want to have lots of pieces, you know, infinitely many, in fact, for this application. So they would make that thickness so small that you could hardly see it, and that's what dx is there to represent. So now the task is to find what is the area of each one of these disks, right? If you, by the way, you can also look this up as disk method on the internet. So the area of each one of these disks is governed by, first of all, the fact that it's a circle, and secondly, the fact that each one of these disks has radius, whatever that green value is. And you have to think this is all over the place, right? So again, there's another radius right there. Well, the radius is basically the functional height. So the radius is the function. And I put it in brackets there because to find the area of any circle, we need to do pi times the radius squared. So the radius squared, and then pi I can leave outside of my integral because it's not dependent on x. So this is really pi r squared. And in our case, the r value is the y value, which is x squared. So pi from 0 to 5, x squared squared dx, which is pi times the integral from 0 to 5 of x to the 4th dx. And then from there you get pi times x to the 5th over 5 evaluated from 0 to 5. And then you get an answer from there. So I guess that's 5 to the 4th. Yeah. So 625 pi. Check my calculations on that. And then 0, when you put that in, that's of course 0. So that is, again, area times units. That you get a volumetric unit, a cubic unit there. And then we're just adding up infinitely many of them. Remember, what integrals are really good at is basically doing the infinite sum as whatever x approaches infinity of f of x, right? So the infinite sum here, and then it just adds all that up, and we know that antiderivatives do the trick for us. So now I'm going to do the same exact thing, except revolving about the y-axis. So now you can imagine what this thing is going to do is create disks going in this direction. And actually, the textbook has a picture of this. I'm just going to flash it to the camera. That is y equals x squared. And then that is the same exact picture revolved about the y-axis. Okay. So now what we're going to do is allow that revolution to happen. But of course, just like in the last lesson where we learned to do dy integration, we'll have to apply that as well. So imagine, for example, that we're going to an x value of 2, which means the y value is, let's do 3, and I want to follow the same one that you just did. 3 and 9. So that's what that point is right there, 3 squared, right? And now we're going to, again, revolve this thing about the y-axis. So there's all kinds of little circular slices going on here. I've drawn the top slice and maybe a middle slice. And 9 again is the top. So we're going to need to find what that radius is. And then we're going to need to do, again, an integral with pi times the radius squared. However, in the case over here, each slice had thickness dx, right? It was a small increment in x. Whereas here, each slice will have a small incremental dy thickness. So we're going to do the integral of pi. We'll deal with these limits in a second, but anyway. So the function, we need to come up with some function of y squared dy. So now to deal with the limit, we're going to be slicing from the top all the way down to 0, and the top in this case is 9. So we're going from 0 to 9, but we need to write a function of y, which means here we need to take the square root of both sides, so we get root y is equal to x. And now when we integrate, it'll be pi times the integral from 0 to 9 of root y squared dy. And that's pi times the integral from 0 to 9 of y dy. And then you go from there. Looks like 81 over 2 pi. So that's going to be the volume of this whole thing. It's not the same as the one done in the textbook if you're looking there. But anyway, that's the volume of this. And there's one third thing that we can do with this, and it's to do what we did last lesson, which is get in a region that's bounded and then revolve it about an axis. So I'm going to do that one as a dx, and the question is going to be the region bounded by the curves y equals x and y equals x squared. So find this region bounded, and then revolve about the x-axis. Okay, so the first thing is I want to get an idea of what's going on here. That's y equals x. That's y equals x squared. You could set these two things equal and find that they meet each other at 0 and at 1. So we're trying to take this little guy here, and then we're going to revolve it about the axis. So it's going to kind of be like a trumpet, but it has conic outside, like a cone on the outside, and it's got this sort of belly inside of it, right? Like a traditional trumpet would. It's almost like a trumpet, just with a conal or a conic exterior. So now we're going to revolve that thing about the x-axis. The problem here is, of course, that there's air in here now. There's going to be space. So what we're going to do is we're going to do the whole thing as if it was just one cone, one block of a cone. In other words, revolving the top around, finding that thing's volume, and then revolving the bottom around, and you can see in here there's a little hole that's been created, so that would be a hole, and then this part would be solid. So basically we'll do the larger integral, pi times, the larger one is x squared dx, going from 0 to 1, and then we'll subtract away pi times the integral from 0 to 1 of the smaller one, which is x squared dx. And again, these are dx's because the slices are going to be thicknesses with respect to x, right? Thicknesses like that. And they're squared because it's pi times the radius squared. And then when you do all those, of course, you'll get yourself an answer. You could combine them to be one integral, which would be 0 to 1 x squared minus x squared dx. It doesn't really matter which one you want to do. But the basic idea is you're taking the larger volume and then subtracting out the hole that's in the middle. So we revolved about the x-axis, we revolved about the y-axis, and then we took a bounded region and revolved that around an axis as well.